Welcome to 13.2, but first I want to go through 13.3 or 13.1, a little bit of the homework. I thought you might be experiencing a little bit of problem with problem maybe 43 and 45. So let's take a look at problem 43. A bag contains 3 red, 5 yellow, 8 blue marbles. How many ways can 2 red, 1 yellow, 2 blue marbles be chosen? So we want to choose 2 red, 1 yellow, and 2 blue from a bag that contains 3 red, 5 yellow, and 8 blue. So how many different ways can that occur? Well, what we're trying to do is get a group of marbles, so I would do a combination. We want to select 2 out of the red, of which there are 3 total. I would take that number of ways of selecting red marbles, and I would multiply it by the number of ways I can select 1 yellow marble from a grand total of 5. And I would multiply that by the combination of the blue, and we have 2 blue that we want to select from a grand total of 8. And that should help you get to your answer. Because we're just looking for groups, you'll use combinations. 45 would be similar. If I want 3 hearts and 2 clubs, we'll think about how many hearts are in a deck, which is a fourth of the deck, or 13 cards. So on this one, I think you'd want to do a grand total of 13 hearts. I'm selecting 3 multiplied by a combination of clubs, and for clubs there's also 13 clubs in a deck, and I want to select 2, and that would give me the number of ways of which those 5 cards could be selected. These 2 numbers, those amounts you're choosing, should add up to the grand total of what you're trying to compose, such as a 5-card hand. So just a little help there on problem 45. So here's 13.2. We're looking at repetitions and circular permutations. So we're going to do just a little quick thing here. And maybe you've done this if you've played Boggo before, or some of those games where you try to make other words, but we're not going to try and make words here. Let's just see how many different ways I can arrange this stuff. So I could have CEA, CAE, I could have AEC, the other one of that, and then I could have EAC and ECA. I think there should be a grand total of 6 there, and yes, it looks like we've got 6 of them. So each of those produce a unique ordering of those 3 letters. But compare that, so we had 6 total here, didn't we? Compare that to the word B. How many different ways can I arrange the letters in the word B and still have some uniqueness? So if I tried to go B-E-E and switch around these E's, it's not going to look any different. So that would not be a unique ordering. However, I could go E-B-E and I could go E-E-B, but that limits the number of ways I can do it. So there's really only 3 ways in which I can arrange those letters. Significantly less than the word ace, where I had all different letters. Here with the repeat, it's going to decrease the permutations that can occur. So that's what we're looking at when we talk about permutations involving repetitions of letters, repetition of any of the items we're trying to select. And then we're going to take a look at what happens when we're working in a circle. So here's the one, permutations with repetition, the number of permutations of n objects of which p are alike. So they're talking about the number of alikeness here, and maybe there are more than one letter of where they are alike, and that would be q. So the formula goes n factorial over p factorial, q factorial. You could have r factorial, s factorial for the number of repetitions that are occurring. And if you want to just write it down again, be my guest. Sometimes it's helpful to write things down and memorize them that way. How many 12-letter patterns can be formed from the letters of the word mathematical? Well, I noticed that there's quite a few repetitions. The letter M is repeated twice. The letter A has 1, 2, 3 times. And anything else? Oh yes, the T. Here we've got a T, two T's. So T is repeated twice, and I think that covers it. If I add up the number of letters in mathematical, I get 12 letters. So if they were unique letters, I would say I have 12 factorial ways of rearranging the word mathematical. 12 factorial would be equivalent to doing a permutation of 12 things, choosing 12, all 12 of them. So 12 factorial would be our total number of ways if everything was unique. However, we know with those repeated letters, it decreases the amount of unique ordering patterns. So I take each letter and I divide by the number of repeats. So M had 2 repeats, so it'd be 2 factorial. A has 3 repeats, so that's a 3 factorial. And T was repeated twice, 2 factorial. And then, just take your calculator and do your factorial, which is underneath that math probability menu. And you should turn out with 19,958,400 for total number of unique orderings. Example number 2, how many 10-letter patterns can be formed from the word proportion? Well, as you can see, there's quite a few repeats again. We've got a P, so 2 P's, an O, an O, an O, 3 O's, 2 R's, boom, boom, oops, and that should be it. 2, 3, 2. Total number of letters in the word proportion, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 total letters. If none were repeated, that would be the number of ways it could be reordered. However, we do have the repeats, so 2 factorial, 3 factorial, divided by 2 factorial. When you put that in your calculator, be sure that you go 10 factorial divided, insert parenthesis because you need all of these things to be your divisor. And then I would just close my parentheses. You do the calculator work, see that you get 151,200. You may want to pause the video and do that calculation, make sure you get there. Okay, what if things are arranged in a circle, like sitting at the table for supper? Here is the little thing from the book. It says if n objects are arranged in a circle, then there are n factorial divided by n, or you could calculate it and say it's n minus 1 factorial permutations of n objects around the circle. So here's just a little note. If a circular object can be flipped over and look the same, the number of permutations must be divided by 2 because it's going to decrease the number of possibilities by 2 or in half. A plain key ring, and by that we mean like there is no key fob on it or anything else like that. Key rings are a little bit tricky because sometimes I think by looking at those keys on the back side, they look different than on the front side. So I'm not sure that's the best example. We'll discuss that one in class a little bit. However, a bracelet without a clasp, so a bracelet with beads, it's going to look the same whether I flip it over or look at it from the top side. And a necklace without a clasp kind of falls in that same category. So if they had beads on them, you may not be able to tell the difference whether they're upside down or right side up. In that case, the formula goes n minus 1 factorial divided by 2. So mainly we're talking about bracelets and necklaces that have beads on them and they don't have a clasp like a starting point. So that brings us into the next topic. If a circular object has a fixed point, which could be considered like a clasp on a necklace or a clasp on a bracelet, you know where their starting point is. Or a keychain that has, or a key ring that has like, some sort of key fob on it. Perhaps it's your remote control opener for the car. That creates a fixed point, and I can order things around that particular fixed point. Then this will be treated like a linear permutation, which is super easy. It just becomes n factorial. So if it has a fixed point, it's n factorial. If there is no fixed point, then it's going to be n minus 1 factorial. So this is for circular items. And this formula is for circular items, but they have a fixed point, which really translates into a linear permutation. Okay? So down at the bottom here we have an artist has a carousel type caddy that holds 14 different colored markers in a circular arrangement. How many ways can those markers be arranged? So if you can imagine, you've got, kind of this cylinder type carousel, and there's spots for holes, and it can hold the markers in it, 14 of them, all different colors. How many different ways can we arrange that? Well, in this caddy, I would assume that there's no fixed point. Like I couldn't determine that right here's my starting point. So there's no fixed point. Since that's the case, this is a circular permutation of which I would do n minus 1 factorial. Since my n was 14 for number of markers, I would have a 14 minus 1 factorial, which in turn would make it 13 factorial. And we can calculate that in the calculator. How about this one? 11 people are seated at a table where one person is seated closest to an exit. How many possible arrangements of people relative to the exit are possible? Well, this exit thing, so if I've got a table and over here is my exit door, and I've got a chair seated there, and around the room, around the table, we've got these chairs. This becomes a fixed point to us, because maybe there's an advantage to sitting next to the exit. And I can distinguish the difference between where people are seated at the table based on this exit point. That creates this as a linear permutation, and I just have to go n factorial. Since there were 11 people seated, we'd have 11 factorial as our answer. 11 factorial as an answer is 11 factorial. I thought I had it calculated. Okay, finally, how many ways can 12 keys on a key ring be arranged? I am going to go circular on this one since there is no beginning, and we're just going to go 12 minus 1 factorial. I believe keys look different whether it's upside down, right side up, so I'm not going to divide by the 2. I'm just going to call it 12 factorial, which reduces to 11 factorial. Now on this last one, how many ways can 12 keys be arranged on a key ring that looks like the below? So we've got this little flashlight or LED light thing going on. That creates a fixed point for us. And maybe I want my car engine key to be my first one after that. Well, that's going to create a bunch of different permutations. This will behave just like a linear one, which will be n factorial. And what do we have? 12 keys. So we're looking at 12 factorial for that particular one. Pretty easy. 13.2 is our assignment that will be coming up in class on Monday. If you are not going to be in class on Monday, here is the assignment. Page 849, 4 through 11 all, 12 through 18 even, and so on. So you could get started on that if you had time, but otherwise, see you guys around. Have a good weekend.